Balancing chemical equations is just something that takes a lot of practice, but I guarantee you're going to dominate. Eventually, we will be masters of balancing chemical equations. And so here's an example. A student suspended copper wire in an aqueous solution of silver nitrate. They noticed a deposit of silver crystals on the copper wire when the copper reacted with the silver nitrate. They recorded their equation, but they did not balance it. All right, so we'll take over from there, huh? Okay, so we've got the skeleton equation, we've got the symbols, but we need to balance. So I usually just start with whatever comes first. Now, I'm going to break this down by ion. So when I look at the original equation that's given all the way over here, I see what comes first? The silver ion. Well, there's one silver ion on the reactant side, and there's one silver ion on the product side. So right now I say silver is all good. Silver is balanced. Now when you get to polyatomic ions, if they stay the same on both sides, it is a huge time saver to balance them as an ion. Rather than splitting this apart and trying to balance the nitrogen atoms and the oxygen atoms, if NO3 stays NO3 on both sides, just think of it as one ion. And so here I have one nitrate ion on the reactant side. No, but on the product side, there's two nitrate ions. Okay, well then I need two nitrates on the reactant side. Well, my only choice is to put a 2 in as a coefficient over here. I cannot do this. Well, then let's just make it a 2. This is a big fat sad face. That I cannot do, because realistically, silver's charge is +1 and nitrate is -1. So that's not going to be a balanced formula. You cannot change subscripts. But if I need 2 nitrate ions, which I do, then you got to go all the way out in front and give it a coefficient of 2. All right, well, that fixed the nitrate situation. By putting the 2 out in front, it doubles everything. So it doubles my groups of nitrate, but it also doubles my silver. Oh, I thought I had the silver. I had one on each side to start with, but again, that's why it's called balancing. So by putting that coefficient in front, it doubled my nitrate, which I wanted, but it also doubled my silver. And so we balance. That's then why we had to go back in and put a 2 by the silver on the product side. So now if I look at all my ions, I've got 2 silver, 2 silver. I've got 2 groups of nitrate. On the product side, I've got 2 groups of nitrate. Then there's 1 copper on the reactant side and 1 copper on the product side. We've got it. Everything is balanced. So that's, I think, the key is that you just work it side to side. And sometimes you put in a coefficient and it fixes one particle and it screws up another. And I guarantee as long as the formulas are written correctly, these things will balance. But it just takes a little working side to side. Let's try some. So number 8, write the balanced chemical equation for the reaction of, okay, so solid carbon. That's just carbon. It's a solid, so I'll put in a little S. The reaction of solid carbon with oxygen gas. Now here's again where it's helpful to know that there are some elements that this is oxygen. It's not bonded to anything else. Some elements are diatomic, and it is a gas. So remember, the diatomic elements are like hydrogen in the upper right-hand corner, and then all the way over on the, or say upper left for hydrogen. On the right-hand corner, it's nitrogen, oxygen, fluorine, chlorine, bromine, So on your periodic table, like in the back of the book, if you want to just kind of like make a circle around those elements and just maybe like make a little symbol somewhere, write an arrow that indicates that these are the diatomic elements. That when these guys are not bonded to anything else, they come in pairs. Now, most of the other elements are just singular atoms, like carbon. All right, so where did I leave off? The reaction of solid carbon with oxygen gas to form carbon monoxide gas. So carbon monoxide, and it is a gas. All right, so the first thing I do is kind of read through my scenario. I'm looking for the reactants and the products. I'm looking for those key words. Something reacts with something, to form, to produce. And I can write it now as just a skeleton equation. I've got the symbols, and I'm ready to balance. So it looks like we've got one carbon on each side, so that's all good. But on the reactant side now, there are 2 atoms of oxygen. So if I want 2 atoms of oxygen on the product side, I got to go all the way out in front. There's my 2 atoms of oxygen, but it also gave me 2 atoms of carbon. Oh, fine. I'll go back and give you 2 atoms of carbon. And I think she's balanced. 2 carbon on each side, 2 oxygen on each side. The little 2, like this little 2 here, the subscript 2, just means that those 2 oxygen atoms are chemically bonded together. If I were writing this as like little particles, maybe I'd have a carbon atom reacts with, this would be like 2 oxygen atoms that are joined together. When I see the 2 out in front, that's like 2 individual particles of carbon monoxide. So that's kind of like this, if I were modeling it as particles. Maybe I'd think of it something like that, where there's still 2 atoms of oxygen. It's just that they're in a totally different arrangement. Now they're separated into separate particles and bonded to a carbon, but they're still present, and that then is the essence of a chemical reaction. All the atoms are still present. Ooh, I should put a 2 here. There's 2 individual carbons. Oh, that is a terrible circle. There, that's a little better. 2 individual atoms of carbon. 2 atoms of oxygen, they're just joined together. And the products still have 2 atoms of carbon and 2 atoms of oxygen, but they're in a totally different arrangement, and they'll have totally new properties on the product side. All right, number 9. Here's a good one. Write the balanced chemical equation for the reaction of glucose, C6, oh boy, H12O6, with oxygen gas, who's still one of these diatomics. Glucose is a sugar, so they're not telling me, but usually this would be a solid, a different form of sugar. And they are hinting that oxygen is a gas. To produce, so here comes my products, carbon dioxide gas. Carbon dioxide is a gas. Ooh, interesting. And water vapor. So water is H2O, which normally is a liquid, but now they're telling me that it's water vapor. That's in the gas phase. Fantastic. All right, let's get after it. Let's balance this thing. All right, I'm going to start with carbon for no other reason, but it comes first. There are 6 carbon on my reactant side, so I need to get 6 carbon on my product side. All right, so we got to go out in front. Let's go to hydrogen next. There are 12 hydrogen on the reactant side, so I need 12 hydrogen on the product side. Last time I checked, 6 times 2 is 12. Oh, brother. Okay, now oxygen, there's oxygen everywhere. All right, well, let's see what we got on the product side, because I don't really want to mess up the product side, because I know that I've got the carbons and the hydrogens all balanced. Okay, so this is 6 times 2. Yikes. That's 12 oxygen. And then here's another 6 oxygen. I'll go like oxygen. That doesn't look like a 0. Okay, so there's a total of 18 oxygen on the product side, which means that I need to get a total of 18 oxygen on the reactant side. How are we going to do this? We've got oxygen in 2 spots on the reactant side. So it might seem as though there would be like different ways to get 18 oxygen. It might kind of seem that way, but I really don't want to put in a coefficient here. I mean, I get that I could, but I don't really want to, because if I put a coefficient in front of that big glucose molecule, not only will it maybe fix my oxygen, but it would also change my carbon and hydrogen. And I don't know if I really want to do that, because right now I've got the 6 carbon and I've got the 12 hydrogen. So if I put a coefficient in front of glucose, now I'm going to have to go back and fix the carbon and hydrogen. I don't think I really want to do that. So instead, I'm going to look at this and say, all right, I'm not going to put a coefficient in front, but here's 6 oxygen. And so I don't want to mess with those. I need to get a total of 18. So if I already have 6, could I then say, what if we just put like 6 right here? And then that would give me 6 times 2 for 12. And I'm not screwing up anything else by putting the 6 in front of the O2. And then here's my other 6 for a total of 18. Ah, yeah, that does work. So there's 6 carbon on each side. There's 12 hydrogen on each side. And there really is a total, oh, crazy. There's a total of 18 oxygen. Here's 6. And then here's another 12. And we just want the total number of atoms to add up on both sides. There's 12 total oxygen on both sides in a very, very different arrangement. But again, that's the beauty of a chemical reaction, is that we've taken all the same atoms but totally rearranged them to form products that have new properties. Again, some of these tricks just take practice, but that's one good trick to kind of put in like your back pocket, that if you've got, like in this case, the oxygen in 2 spots, maybe shy away from putting the coefficient in front of a particle that's also going to change other elements. But I guarantee, as long as you have the formulas written correctly, these things will always balance.